My talk today is kind of focused a little bit more on the technical side for how we're going to analyze for PFAS. My name is Sarah Dowd. I am an application scientist for Waters Corporation. We make scientific instruments, including LCs and mass specs. My expertise is on the mass spec side of things. So please, if you have any questions about the analysis, feel free to drop them in the Q&A. So I'm going to go quickly through this slide because I'm pretty sure most folks that are attending this conference are probably sick of hearing about PFAS or are experts themselves. So I don't need to tell you that they're everywhere, they bioaccumulate, nobody wants to see them anymore. But really, for the sake of my talk, what's really important about PFAS is how challenging they are to analyze. We've got, as far as we know, there could be 4,000 to 6,000 known PFAS compounds. So these polyfluorinated compounds are there's so many different chemistries available, and there's some we haven't even discovered yet. And of course, when it comes to analyzing them, we've got lists of targeted PFAS and EPA methods, but the detection limits on those keep getting lower. So certainly for drinking water, we're looking at parts per trillion detection limits for these compounds. And if it were up to the regulatory agencies, it would probably be even lower. So that creates a real test for analytical chemists in terms of being able to reliably detect these compounds, even with their different types of chemistries and at these low levels. So I'm going to talk a little bit about two different ionization techniques. And the first one's kind of focused in on our traditional PFAS compounds, the carboxylic acids, the sulfonates that we're typically analyzing using LCMS. And what I'm going to talk about here is using a different ionization mechanism. So for us to detect these compounds with a mass spectrometer, we have to get our compounds into the gas phase and they have to be charged. So traditionally, we do this with electrospray ionization. That's where you flow liquid through a charged capillary for PFAS, it's traditionally negative ionization. And you're typically running at a flow rate, probably about 0.5 ml per minute in the LC side of things. So one of the things about electrospray, though, is it actually doesn't have very high ionization efficiency. So this graph here is comparing traditional high flow rate electrospray compared to a lower flow rate like nanospray. And we're seeing, not all that much improvement in terms of signal despite an increase in the consumed analyte with electrospray. So we're typically looking at lower flow rates, we see a higher ionization efficiency. So when the pharmaceutical companies are trying to get their really low detection limits in matrix, they're typically using something like low flow rates in nanospray. But I can tell you from experience, trying to operate nanospray is a pain in the butt. Trying to know if there's a leak when you're flowing at, microliters per minute and making good connections that way, it's just not efficient. And the run times on your LC you're going to be talking about 30 to 60 minutes instead of 10 to 15. So the takeaway from this slide is just that ESI has low desolvation efficiency. It's producing large droplets with relatively low surface charge area, and that's inefficient in producing our gas phase ions. So to kind of address that problem, a couple years ago, Waters introduced an alternative ionization mode called Unispray. And on our instruments, we have a swappable ionization source. So it's really easy to go from electrospray to Unispray. It's just a door on a hinge. You can take it off, swap the other one back on. And how Unispray works is it's a little bit between electrospray ionization and APCI, or atmospheric pressure chemical ionization, where instead of having a charged capillary that the flow is coming through, we're going to leave that probe, or the capillary probe where the liquid's introduced, grounded, and instead apply our voltage to a target pin. So it's a stainless steel pin shown here in the diagram. And so what's going to happen is our flow from the LC side of things is going to hit this pin, and having those interactions with the charged surface actually increases the desolvation efficiency. So just like in electrospray, we're getting large droplets from our liquid, but those collisions with that target pin helps create smaller droplets, and that leads to improved desolvation. The other thing we see with this design is that we get kind of what we call the Coanda effect, which is what you see if like you put a spoon into a flow of liquid, is that we get this wrapping around of the flow as well. So we get a little bit of directed flow into our sample cone. And the result of this, at least looking at some of the PFAS compounds, is that we do tend to see an increase in both in response and signal to noise using this ionization source. So this is looking at PFOA, PFOS, PFNA, and for all of them at the same concentration level, same injection volume, we're seeing, great increases in terms of our signal to noise with the Unispray source compared to electrospray. And that increase in signal to noise is pretty reproducible across the different kind of traditional targeted PFAS compounds. PFBA, for instance, we see quite an increase in the signal to noise value compared to electrospray. In this graph, 1 would be the same signal to noise for the Unispray to electrospray. And the only ones we really see, we see comparable or better signal to noise with the Unispray source. So that's really kind of exciting. And when we actually get into looking at real data, it's actually important at kind of those low limits of detection that we're interested in, like the 1 part per trillion samples. So even looking at our low end of our calibration curve, this is actually probably a good example to see many advantages to the Unispray analysis. So looking at this calibration point for perfluorohexanoic sulfonate, the Unispray chromatograms are on the left, electrospray is on the right. And the top transition is our quantification ion, and the bottom is our qualifier. So usually for us to say that this compound is detected, we need to see traces in both. So you can see with the electrospray, we're missing that qualification ion. So that qual ion peak is missing, but we do see it in Unispray. So we could call this bottom of our calibration point an acceptable detection. The other thing that's kind of exciting in this data too is if you look at, the top trace here for our quantification ions, if you look in the Unispray data, we can start to see the kind of the branched isomers of the PFHXS that are just completely missing with our electrospray data. So those branched isomers aren't detected. So a lot of the PFAS methods are starting to look more at these branched isomers as our total PFAS numbers. So being able to detect them even at low limits is important. So I'm going to switch gears a little bit and go away from kind of the traditional PFAS, semi-volatile compounds, and now look at how we can look at some of the emerging PFAS. So potentially some of the actual precursors to the traditional PFAS that we're looking at. And so these are going to be our neutral and volatile PFAS, which aren't going to be as happy in a liquid chromatography experiment. So a lot of these, there has been some work done on GCMS for. And I decided I was going to test them with our atmospheric pressure GC ionization source. So just like our Unispray source is a swappable option, we also have this atmospheric pressure GC source, which can go on the front of our mass spectrometers. And this links up with a traditional GC, and it's going to maintain all of your traditional GC benefits, reproducible retention times, don't have to make mobile phases because I get sick of making mobile phases. But it actually, because it's atmospheric pressure and the way it works, which I'll get into in the next slide, we've got a lot of advantages compared to traditional EI MS with a vacuum source. The first one of which is that we can use faster flow rates in our gas. We can actually use nitrogen as a carrier gas, which I don't know if anyone else's lab is having this problem, but in my lab, we can't get helium anymore. So having nitrogen as an option is actually really appealing. And what's really important for this analysis is that we get a softer ionization. So how APGC works is it's actually more similar to atmospheric pressure chemical ionization. So this is all atmospheric pressure, there's no vacuum source. And what's going to happen is we actually introduce even more nitrogen into the source. So we've got a makeup gas that flows coaxially with our GC column in the heated transfer line. And that just keeps everything moving towards the mass spec. And then we have a corona pin within the right in front of the sample cone that charges the nitrogen in the source. And so as our compounds start to come off our GC column, they interact with that charged plasma and they get directed into the mass spec. And I really like this comparison looking at, one of the target compounds that we're thinking is going to be one of the kind of the emerging PFAS is a fluorotelmer alcohol, 8,2-FTOH here. This one, it's never going to go well in an LC-MS with electrospray. We're just not going to see it. And the top graph here is actually, or the top spectrum is from the NIST library for this entry. So with a vacuum source EI mass spec, this compound completely falls apart. So the intact mass for this would be 464, which you can see there's very little of that mass to charge detected here. And instead, it's almost all fragment ions. By comparison, with my APGC source, I have mostly intact molecule. So I have my, my fluorotelmer alcohol adding a proton to, so I see mass to charge 464 ion, and I actually see it adducted with a water molecule as well. So this is really, really exciting for creating mass spec analysis, because I know what my compound is. And when I'm generating MS methods, starting with an intact precursor, gives me a lot of hope for getting kind of the low sensitivity that we might need for these compounds. And this is just kind of some new data that we're working on. It's very preliminary at this point, but looking at, some of these fluorotelmer alcohols, got a 1 microliter injection onto my GC of a 0.02 picogram per microliter standard. So 20 femtograms on column. I have very clear peaks in actually 3 transitions here. And I can get strong linearity across a calibration curve, looking at, this 0.02 up to 50 picograms per microliter.
3 minutes remaining.
Alrighty. And I just wanted to show a couple of other examples, chromatograms from other kind of related compounds to that fluorotelmer alcohol. So this would be some of the fluorotelmer acrylates, which again, this is 50 femtograms on column. So we're looking at very low levels of these compounds because we don't know what the regulations are going to be. So having the ability to go lower is always exciting. And the last example for the APGC work is looking at the sulfonamide ethanols. So these are ones that are typically listed in some of the targeted LCMS methods, or if they're not, they might be. I think they're included in the new 1637 or 1677, whatever the new EPA method is. And I know my colleagues struggle with these on LCMS, and they just absolutely lit up on the APGC. So this is 20 femtograms on column, and I've got giant peaks. All right, so just to kind of wrap up, the APGC stuff is very new, but the PFAS analysis we have worked up into an application note. So if anyone's looking for more details about that, the link is included here, and I think there are copies of all slides provided. And finally, I would like to thank some of the other people who worked on this, my colleagues, Carrie, Stuart, and Doug, because I definitely didn't do it alone. And I'll thank you all for your attention.